Hello, everyone. We are moving now to a very important session of our technical program for Micro 54 this year, the awards session, the award ceremonies. This is a very high-level agenda of this session. First, we will start with a few minutes from Professor Zhuhai on the recent loss of Guangzhou. Then we will move to the Best Paper Award and other awards related to this year's edition. Then the Student Research Competition winners will be announced. Micro Hall of Fame inductees for this year. Then the Micro Test of Time Award winners. And then we will conclude this session with the presentation of the Bob Rao Award on microarchitectural innovation. Guri, you can already start. I'm stopping. Please go ahead.
Thank you. Thank you. I'd like to take this moment to remember Guangzhou, one of the distinguished members, longtime members of our community that we lost last month. Guang was born in China. He got his bachelor from Tsinghua in 1965, and unfortunately suffered a lot in the Cultural Revolution after that. He was one of the first Chinese students to be selected to go abroad after the Nixon-Mao Hangzhou Summit, and he joined MIT in 1980 to study with Jack Dennis. He was the first person from mainland China since the Cultural Revolution to receive a PhD in computer science from MIT. After graduation, he worked briefly at the Philips Research Labs for a couple of years. Then he joined the faculty at McGill, where he built a eminent research group, made several research contributions. Then moved to the University of Delaware after that, where he retired as a distinguished professor. He graduated more than 30 PhDs and mentored more than 30 postdocs. Made significant contributions to compilation techniques for static data flow, VLIW, ILP, and multi-threaded machines. For his numerous contributions, he was recognized as an ACM Fellow, an IEEE Fellow, and he was a very frequent contributor to Micro. He would attend all the Micros when Micro was small, 100 people attending. And in 2017, he was the recipient of the Rao Award for contributions to compiler techniques and microarchitectures for instruction level and thread level parallel computing. It's a great loss for all of us. Guy was a very decent person, very decent human being, very distinguished scientist, and it's a great sorrow to have lost him. Thank you.
Thank you, Guri. Amer?
Sure. Can we see the slides?
Yes.
All right. Hello, everybody. I'm Amer, and Jishin's here as well. We have a couple of awards lined up as part of the technical program. First, the Best Paper Award. We had a paper session devoted to the best paper candidates. These were the top 4 ranked papers with consensus nomination from the paper reviewers. As part of the best paper selection process, we formed a committee. The best paper selection committee was chaired by Chris, and we had Chris Wilkerson, and we had 6 other members from the technical program committee. So After deliberation across them, they ended up arriving at the vote was very, very close. To that end, we have decided that we are going to be awarding both a runner-up award and a best paper award. So first, from the runner-up, our best paper runner-up will be awarded to TIP, Time Proportional Instruction Profiling, by Bjorn Gottschall, Levin Eckert, and Magnus Jarrett. Congratulations, the three of you, on your runner-up award.
Thank you very much.
Next, let's Jishin.
Okay, next is our best paper award. So our best paper award will goes to Apollo. So that's best paper award goes to Apollo. The authors are Zhiyao Xie, Xiaoqing Xu, Joshua Knell, Kumar Guru, Palance Wani, Nicholas Herbert, Zhang Hu, Huan Rui Yang, Ian Chen, Shah Das. Congratulations to all for the best paper award.
Thank you. Thank you very much.
Congratulations.
Good job. Okay, the next portion of the award, as Jish and I had mentioned as part of our opening remarks, this was the first year that we had a reviewing the reviewer concept, where the authors of all submitted papers had the opportunity to provide feedback on the reviews received. We had a record number of reviews performed at Micro this year, over 2,500, and we received 80% of the reviews, feedback on the reviews that were conducted. This was a great initiative to help us assess the state of the review process, but it also allowed us to acknowledge and recognize those reviewers that went above and beyond to provide feedback, constructive, quality, and insightful feedback. Here is basically the S curve of the reviewers average. We had 5 questions. One question was, considering everything, how would you rate the overall quality of the review? So what we would like to do is to recognize the top 3 reviewers from our 122 program committee for providing insightful, constructive, and quality feedback. And those 3 are Sagala Ghost, Arthur Perez, and Yakub Zephyr. We thank you and the rest of the technical program committee, for your hard work and providing us with the review process and to select the 94 papers as part of our program this year. Now, I would like to hand it over to Gennady.
Yes, thank you.
All right, go ahead. Should I advance on? So as part of Micro, as part of Micro, we had the artifact evaluation. And go ahead, Kenna.
Yeah, it's a great pleasure to introduce, the artifact evaluation, process to Micro the first time this year, and also for the first time we had a distinguished artifact award this year. So it's a great pleasure to award it to the paper titled "A Hardware Accelerator for Protocol Buffers." So we just establishing the process for deciding, what the distinguished artifact should have. But in this case, it was a very easy decision. It was supported by all the evaluators of this paper, and all the it was the rank very high by all of the program committee members. So in the future, we hope to have even more papers submitted and potentially multiple distinguished awards, but we want to set up bar high, and this paper definitely meet the bar. So congratulations to the authors. Thank you.
Thank you. With that, we end this portion of the award session.
Thank you, Amer. Now it's time for the SRC competition winners. Osman, are you connected?
Okay. All right. I and Yasuko would like to thank all the reviewers for the hard work. Basically, what the student research competition is that it's a unique forum for undergraduate and graduate students, two different avenues, to present their original research before a panel of judges and attendees. And so there to foster the communication, visual, organizational, presentation skills. And we, and the ACM, rewards the top three, let's say, presenters out of the submissions to the undergraduate and graduate tracks. So for that, going straight to undergraduate winners, the third place is Jim Zhu for his presentation titled CNN-based position decoding from calcium images. And second place is Shabnam Sheikna in her presentation titled Lavia, locality-aware vector indexed architecture for efficient graph processing. Congratulations to both. Therefore, our first undergraduate winner goes to Shishin Song from University of Michigan for a presentation titled HWC, Profile Guided Branch Target Buffer Replacement for Data Center Applications. Heartfelt congratulations, Shishin. And so this concludes the undergraduate part of the awards ceremony. As we go to the graduate part, we have in third place Liu Liu with a title of the presentation, Transformers Acceleration with Dynamic Sparse Attention. Second place is Nelu Shivaprakash Kalani from IIT Kanpur, titled Instruction Criticality-Based Energy Efficient Hardware Data Prefetching. And first place, and our winner in the graduate category is Taran Solansky, also from IIT Kanpur, for the presentation titled SpecPref, High-Performing Speculative Attacks Resilient Hardware Prefetchers. So congratulations to all the 6 winners. Congratulations to the undergraduate winner Shishin and graduate winner Taran. Thank you, and this concludes the SRC award ceremony.
Thank you very much, Osman and Yasuko, as well as all the members of your committee for the hard work during the last months on the SRC competition. Now it's time for the Micro Hall of Fame new inductees. Eric Altman. Eric, you can share your screen. Thank you.
Yes, thank you very much. And so this year, we have a record 10 inductees into the Micro Hall of Fame. And so I'm very glad to introduce all of them and recognize their contributions. For those who may not know, that it's a basic to state and harder to do, of course, a requirement to enter the Hall of Fame, basically have 8 papers published cumulatively in micro over any number of years. And so we have 10 people today who we're recognizing who've met that standard. And the first one is Pradeep Bose of Ibm. So congratulations, Pradeep, on this excellent accomplishment. As for all of the recipients, I outline on the bottom here the sort of years when they've had papers. So you can see Pradeep spans almost exactly 20 years from 2002 to this year, and you can see his co-authors on the top here. So he's had quite a broad set of co-authors over time, and Pradeep has certainly been a major part of the community. So congratulations, Pradeep. Next is Zeshan Chisti of Intel. Zeshan, of course, has also achieved this milestone, and to show his papers, he's also spread over almost 20 years and going back to 2003, and again has a very broad set of co-authors, and we congratulate you, Zeshan. Our third inductee is Chang-Hee Zhang, and Chang-Hee has been about a dozen years of contributions. You can see all of his co-authors here. He's had a couple of years recently, including this year with 2 papers. So that's a very difficult thing to do. So congratulations. Moving along, we have Jeremy S. Kim, who was at CMU, who's now at ETH Zurich. Jeremy has done this at lightning speed, starting in 2017, and with 3 papers this year, 4 papers last year. So a very impressive accomplishment in a very short time, Jeremy. Congratulations. Fifth is Sean Lee, aka Sean, who's currently at Facebook. And he started in terms of micro publications back in 2000 with some of his collaborators at Michigan, and then has a paper this year. So very nice work, Sean. Congratulations. Next is Gilles Pocam from Intel. Gilles has also been active for about a dozen years in terms of publishing micro papers. Last year, he had 4 papers. This year, he has another one. So he's reached the plateau and has done a lot of excellent work with a broad set of people, as you can see here, as indicated by his collaborators. So congratulations, Gilles. Next, we have Zhuhai Chan of USC, the University of Southern California. Zhuhai has also been doing this over a little less than a dozen years, starting with Josep Torellis and others at UIUC, and now he's been at USC for a number of years, and has published up to 3 papers in 2018, and as typical of I think virtually all of these inductees, lots of strong co-authors. So congratulations, Zhuhai. Next, we have Srinivas Subramoni, who was one of the very interesting panelists that we saw yesterday, discussing the perspectives on microarchitecture research from around the world. And of course, he was coming from Bangalore, India. So congratulations, Srinivas, and he actually has 4 papers this year. That's an amazing accomplishment. Congratulations. I mean, this actually looks sort of like an exponential curve, so I don't know if that means you're going to have 8 next year. I think that would be virtually impossible, but congratulations. This is an amazing accomplishment, and thank you for all the very impressive work over these years. Oops, well, that's not quite what I meant to do. Sorry about that. Apologize for the technical glitch. Okay. Next, we have Jun Yang, who was the micro PC co-chair last year, and she's at the University of Pittsburgh. And she's been doing this for about 20 years. So many papers over many years. This year, actually 2 papers. So and another really nice accomplishment. Congratulations, June. And finally, our 10th inductee this year, if you've been keeping count, is Yutao Zhang, also at the University of Pittsburgh, and also over basically a 20-plus year period, and a number of publications joint with June, who we just saw. So very nice work, and actually 4 papers this year. So very impressive. Congratulations. And I'll just show everybody once more so that we can appreciate them, and hearty congratulations to all of you. You'll be receiving plaques in the next couple of weeks or so, I hope, with a formal recognition, but I'm glad we can recognize you with everyone at the conference here. And just to show, we will be publishing this information on the SIG Micro website, which Saugata Goes maintains so nicely. You can see all the people who reached 8 publications this year highlighted in yellow, and four of the people this year actually had 2 or more papers, so they actually jumped right up to 9. And on the microsite, you can see everybody all the way up to our most prolific contributors over the years. I'm sure this is going by too fast for everyone to digest, but Yale Pat has just reached the 50 plateau this year with 2 papers this year. So wow, that's really amazing. Oner Mutlu has 6 papers this year, so he's at 44. So interesting competition there. So congratulations, everybody. You can see this stuff in more detail on the SIG Micro site. I also would like to just add quickly, I had the committee which is looking at the SIG Micro Distinguished Service Award. We got, unfortunately, a slightly later start than would have been ideal, and we hope to be announcing something over the next few weeks there, but stay tuned. We want to recognize people who've really contributed significantly to the micro community. So thank you.
Thank you, Eric. Thank you, and congratulations to the new inductees. Now we're moving to the Test of Time Award. Ritu,
yep.
You can share your screen. Thank you.
Okay, it's absolutely my great pleasure and honor to present the Micro Test of Time Award. This is the most influence. It's about the papers which had most influence over the last 15 years or so and have high impact on the micro community. So this year we have 2 papers which are the joint winners and absolutely my favorite papers. So not to keep the suspense any longer. So I'm gonna just do it in alphabetical order of the title, of the paper title. So the first Test of Time award goes to Razer, a low power pipeline based on circuit level timing speculation. And the authors of this very foundational work are Dan Ernst, Namsum King, Siddharth Das, Sanjay Pant, Rajiv Rao, Toan Pham, Conrad Ziesler, David Blau, Todd Austin, Christian Flotner, and Trevor Much. Razer introduced the revolutionary ideas that allow operation at a voltage lower than worst case design and combat the increasing design god bands. This foundational work is exemplary of the high impact possible from architecture and circuit cross-cutting research. With that, I would love to hear some prospective remarks from the authors who are present here today as panelists.
Great, thank you, Ritu. First, on behalf of all of us who worked at Razer, we'd like to thank the awards committee and the nominators for this recognition. In any undertaking, it's always really gratifying to hear that something you did had an impact. So again, thank you very much. Really, Razer at its core was about using architectural techniques to move from design for worst case to designing for a more common case or average case. And really, as we move through this era where efficiency gains are getting a lot harder to achieve, this is the philosophy that's starting to show up in a lot of places. As an example, DDR5 coming soon is going to use on-die ECC in order to make their design phases and margins easier, all the way up to system level things like data center disaggregation. So as these kinds of techniques are really kind of by definition cross-cutting areas, make sure you're talking to people in other areas. And in the interest of looking across, I think I'm going to pass the virtual mic to a few of my colleagues to hear their perspectives. So Nam, you want to take it up?
Yeah, thank you, Dan. And I think this Test of Time award with the Razer is a proof that circuit and architecture cross-cutting research is getting the due recognition. from the community, along with the broadcast that received the ISCA Influential Award a few years ago. And that said, I really want to thank Trav, David, and Todd, who inspired me and the other graduate students back then with such a great research vision. Thank you.
Okay, I'll now take the virtual mic from Nam. So just as Dan and Nam, I want to start by thanking the awards committee for recognizing this work. Also wanted to comment a little bit about how much this research actually benefited from direct collaboration with industry, starting from the very early days of research, very early days of Razer. Apologize about the video. For some reason, the video is not just not turning on for me. For one, it actually helped us have a razor sharp focus, well, no pun intended there, on real world constraints, and therefore help to shape future Razer versions in a way that were much more friendly towards industry adoption. And in that regard, I will particularly like to acknowledge my mentor at ARM, David Bull, who some of you might actually know as the lead designer of the ARM9 CPU core, whose contributions to Razer have been particularly stellar. Taking an academic idea and making it real is more often than not just pure hard slog, but very rewarding in the long run. And I think this award really proves that. So thank you again for this. Over to you, David.
Yeah, thank you, Siddharth. It's a great pleasure to receive this award, and it's been a great pleasure working with all of the co-authors and across different cross-cutting technologies and fields. Just for a little history, I thought it might be interesting to see how Razer started. I started working on Razer when I was actually looking at dynamic voltage and frequency scaling, or DVFS. And I really did at the time, I didn't really like canary circuits and their mistracking. And so the goal was to try to find something more accurate. And then I saw a talk by Todd on DIVA, and I thought that was a very interesting idea. And so then we actually tried that to see if we could use that for voltage scaling and reduce the margins. And I remember that Siddharth was doing that. And actually we found out that it couldn't really work because the overhead of using an additional core, even a small one, was too large. And so we were actually stuck for a little while. So then what happened is that we had two kind of realizations that I think then finally led us to the Razer work. One was that we realized that delay, that we actually really only needed to worry about delay failures because voltage scaling only changes delay and not the functionality of the circuit. And the other one was that we can still latch signals after they come after the clock edge, which actually turns out that other people have also looked at that, but we didn't know that because we hadn't really read all that much on this topic. So then working on the whiteboard with students, we came up with the Razer Shadow Latch, which was really what sort of catapulted the initial work and then gave some credence to the idea that we could actually cut margins out and remove those. And we immediately kind of knew that we had something with some potential. So looking back, it's just interesting to see how innovation happens. I believe Razer has not been necessarily the most practical idea, but I hope and think that it has actually generated other useful and interesting techniques. And it certainly has been a great collaborating with these great co-authors. So thank you. And it's over to Todd as our last person.
Thanks, David. Thank you. And thank you very much to the committee for this. This Razer is, it's such an awesome that I got to work on this. I really thank all my colleagues for this. This was an amazing project. But I want to just take a brief moment and tell you this. Sometimes when you work on a paper, you get a really great result like this one, but sometimes it sort of changes the way you approach research. And that was really true for this particular Razer paper. At the time, the idea that you could not finish completing circuits with worst case timing was something that was, people had kind of dipped around in it a little bit to try to figure out if they could lower voltages a little bit more, but no one was ever really talking about recovering stuff. And so it was very early on, I found that you get sort of this very sort of almost heretical response, like you cannot do this stuff. It's not possible. And it really, it formed what I like to call a rule-breaking approach to research. And I use this time and time and time again, where the basic idea is one, find a rule that nobody breaks. And it's probably in the first chapter of any textbook, right? worst case design timing, etc. You cannot hack, there's, etc. You cannot stop hacking, etc. 2, break that rule and figure out what happens. It's really 2 things. Either figure out why that rule is so important and you should never break that rule again, or you'll stumble across something that's really amazing that has been hidden because people are so entrenched in these rules. And then the other thing I really love about what Razer taught me and what I love about rule breaking research is a lot of people don't like the work, right? And I think one of the things you need to have for research to really be moving in the right direction is there needs to be a constituency that doesn't like the work, right? I always tell my students that the thing about cutting edge research is it cuts. And the idea that people think what you're doing is wrong is really, in essence, kind of an indication to the researcher that maybe what you're doing is right. So, this is why I hold this paper so dear. And thank you so much for this award. I really appreciate it.
Thank you, all of you. This is amazing work, and hearing your perspective was so much fun. And like it's giving all our new students a lot of inspiration how to go about their research. Thank you. And our next paper is equally impactful and really an awesome paper. In fact, I have done research based on it. So let's see which one is this one. This is single ISA heterogeneous multi-core architecture, the potential for processor power reduction. This is our joint Micro Test of Time Award winner. The authors for this paper are Rakesh Kumar, Keith Farkas, Norm Jopi, Partha Ranganathan, and Dean Tulson. Congratulations on this award. This paper introduced the idea of single ISA multi-core processor architecture. The simple but powerful idea has had tremendous impact on commercial computer systems, including ARM's Big Little, Apple Silicon, Intel Lakefield, and Alder Lake, etc. This foundational work has inspired numerous academic projects on heterogeneous systems. With that, I would pass the mic to Rakesh, who's gonna give us some prospective remarks, and I think he's presenting some slides on this too. Rakesh, are you here?
Yeah, thank you, Ritu. Yes, so we'll do this conventionally. We started this work in summer of 2002. So for the younger people in the audience, summer of 2002 was one where the power had increased exponentially and was really the first order concern. By that time, the most effective technique for power reduction till then, that was voltage scaling, had also stopped becoming very effective. So the voltages had essentially stopped scaling down. And the third trend related to power was that static power, which was not too much of a concern earlier, had also started becoming a concern. So, so you had to not only reduce dynamic power, but also static power. And essentially, it was very clear that you needed dramatically more effective power reduction techniques in order for performance scaling to continue. Simultaneously, there was another trend emerging, and that trend was multi-cores. It's so bizarre that I used to hear stories from my senior colleagues about in my days, and now I'm telling stories about in my days, because multi-cores, which are so common now, in summer of 2002, there were exactly 2 commercial multi-core processors then. So there was IBM Power 4, and then there was essentially Magic from Sun. And there were 2 research prototypes that were not implemented. So, but there was enough evidence that there was technical and commercial feasibility in putting multiple cores on the same die. So these are the 2 sort of 2 trends that were characterizing that time. So in that context, we essentially observed that different applications and different phases within application tend to have dramatically different behavior in terms of how they use processors. So there are applications that have a lot of parallelism. So instruction level parallelism, data level parallelism, memory level parallelism, and these applications when you run them on, let's say, some high performance core, perhaps the core takes up a lot of power, you are using this core the way it was designed. So these applications or application phases are using all the resources on the core. Yes, it's consuming a lot of area. Yes, it's consuming a lot of power, but the core is worth it. But at the same time, there are large number of applications and large number of phases, large fraction of phases within an application that really don't have that much parallelism, that don't have either instructional parallelism or memory level parallelism or data level parallelism, and they're using only a fraction of resources. Now think about it. So you're taking an application that perhaps is a giant jump table, and you're running it on a processor that consumes 100 to 150 watts, and it's consuming only a small fraction of the resources. You're essentially unnecessarily wasting the area and power. So extreme inefficiency. So this essentially gave us the idea of saving power using multi-cores. So the idea was very simple, that if you had an application or an application phase that was going to use only a fraction of the power or a fraction of the resources on the original design, don't run on it. Don't run that application or application phase on the large core. Instead, run that application on a small core that really has only as many resources as the application needs at that time. So no wastage, no extraneous stuff, just exact fit for that application. Furthermore, if the core is indeed small, then perhaps you can put both the large core and the small core on the same die without really increasing your chip area or chip power much. Furthermore, if you're running this application phase on the small core, you could power down the large core completely. Once you power it down completely, you neither have dynamic power nor static power, and most of the power was, if the power ratio between the two was significant, then you have significantly reduced the chip power. Stated differently, essentially what we were proposing was a single ISA heterogeneous multi-core architecture, where the application kept ping-ponging from one core to another, such that it was always running on a core that was the right fit for that application, and all other cores were powered off completely. This was very effective. Essentially, we observed that you could have up to a factor of 3 reduction in power. There were immediate follow-up works from companies like Intel, IBM. They observed that this was giving 4 to 6x EPI reduction, much more than any other technique. So really there was very interesting quick follow-up to establish how promising this could be. And then the idea just took off. So took off, and subsequently it has had significant commercial impact. So by some measure, single ISA heterogeneous multi-cores now power most mobile phones that you can find. So ARM has been doing this in big. LITTLE for quite some time. Apple transitioned to this after A12. So the iPhones and Android phones, they both use it. Gradually, so while it started in the mobile domain, it also started creeping upwards in terms of the kind of system. So now it has moved into laptops, tablets, iPads, etc. So it ended up having a significant commercial impact, we believe, because of not only how significant the benefits were, but also how simple the idea was. So that was really nice to see how it happened. And commercial success is just one measure of work that you do, especially in academia. We also like the fact that it ended up spawning a large number of projects at different levels of the compute stack in heterogeneous systems. What was particularly gratifying was that a large fraction of the citations, a large number of times when this work is referred, is not from the computer architecture community. It's from these very different clever ideas that people come up with, where they're either exploiting the inter and application or inter and intra application diversity, or where they're using the heterogeneity of hardware resources for power, performance. I've seen people do this for reliability. I've seen people do this for security. So it's just it's very interesting to see the different creative ways in which this was used. Looking forward, I think there are many other avenues of research that are yet to be explored. I don't think that we really understand the potential of this kind of approach fully. So consider a certain power, performance, area, cost, time to market design point. For that particular design point, what's the right way to build a heterogeneous system? Should you be using generational heterogeneity, something that we performed our initial evaluations for? Or should you use market segment-based heterogeneity that allows you to essentially keep your costs down? Or should you do custom design, which is something we have seen some of the latest adopters to be using? Then what's the right level of heterogeneity? Should you have two types, 3 types, 4 types of heterogeneity? What's the right nature of heterogeneity? We have single ISA, but there has been work showing that single ISA may be unnecessarily constraining. Perhaps relaxing the constraint is useful. Similarly, a lot of heterogeneous systems, both commercial and academic, have monotonic systems. But so strictly, one is a high performance core and another is low performance core or high efficiency core. But you can imagine fat pipelines with small caches and thin pipeline with fat caches, for example, where there's a non-monotonic relationship. Similarly, we have seen this being useful in context of lower end systems, but how about higher end systems, so servers and data centers? So finally, the most important part, the people involved. We would really like to thank ACM SIG-Micro and Micro Test of Time Committee for this award. We'd also like to thank the computer architecture and the entire computer systems community for welcoming, adopting, cultivating this idea, which really is what ultimately led to this award. At a personal level, I would like to thank my collaborators, Keith Farkas, Norman Juppy, Partha Nathan, and Dee Towson. They are rock stars, but more than that, they're also wonderful people. I have over time, there are so many things I've learned from them about computer architecture, about life, and there are many ways in which I try to emulate them even to this day and going forward. So thank you, and thank you, everyone.
Congratulations to all the authors of the 2 papers. Thank you, Ritu, and your committee for the hard work.
Thanks, Rakesh.
So now we can move to Guri Sohi again for the presentation of the Bubra Award.
Thank you, Dimitri. So it's my pleasure as chair of the B. Ramakrishna Rao Award Committee to give this year's presentation. So this award is given in recognition of significant contributions in the field of computer microarchitecture and compiler code generation. This award was set up in 2010 through the dedicated effort of a group of individuals that are listed over here who put in the effort to get the process going, but also contributed to the endowment that supports the honorarium for the award. So, and it is also, funded by HP and IEEE Computer Society, SIG-Micro, and several individual contributors who've chosen to remain anonymous. So Bob was a giant of our field. He got his bachelor from IIT, and then he came to Stanford, where he got his master's and PhD degrees. And he was the recipient of the Eckhart Berkeley Award and a fellow of both the IEEE and ACM. He, after graduating from Stanford, he joined the faculty at Illinois for a while. And then after that, he left after a couple of years to go back to Stanford and then go on to industry. He was at TRW, ESL, and then he had numerous research publications in the area of PLIW, high performance computing, automated computer system design. He co-founded Sidrum, which was, and the chief architect of the Sidra 5 mini supercomputer. And it was one of the first VLAW architectures. And also it had this conflict-free memory system using hashing. When Sidrum folded, he joined Hewlett-Packard and started HP Labs research program in VLIW and ILP, which then eventually led to the EPIC architecture, HP Plato and the Intel HP EPIC IA64 architecture. And we lost him in 2002, shortly after he received the Eckerd Markle Award after losing a battle with cancer. So this year's award committee was Sandhya, Babak, Mahmood, and unfortunately Guang Ga, who was also on the award committee, was unable to participate. And I chaired the committee. And this year's winner is Daniel Jimenez. Daniel is being recognized for his contributions to neural branch prediction in microprocessors. I remember Daniel's early presentation when he first presented this stuff, and I said, this is crazy stuff. No one's ever going to use it. Boy, was I wrong. It is now found in numerous commercial microprocessors that try and get higher and higher performance by building better and better branch predictors. So it's my pleasure to present the certificate virtually. There's also a check with it that Daniel, I guess, get virtually, physically sometime. I can give it virtually now. It's my pleasure to present Daniel Jimenez as the recipient of this year's winner of the RA Award. Congratulations, Daniel.
Thank you, Gary. So I have a little presentation. Hopefully I can share the right one. You see that?
Yes, we can.
Thank you. Right.
And Daniel, you can take your time. Congratulations, first of all, and then you can take your time because we will start the next two sessions after you are done with your presentation.
Okay, thank you, Dimitri. So thank you to the person who nominated me and the endorsers and the award committee. As Gary said, this is for contributions to neural branch prediction in microprocessors. So I thought I'd indulge myself in saying a little bit about what I think is important to our field and then talking more self-servingly about myself. So my perspective on microarchitecture research, I think core microarchitecture research is hard, but it's still very important. So folks that are working on core microarchitecture research, don't get discouraged. It's very important. Dennard scaling is done. Core microarchitecture research is really our only hope for improvements in single thread performance. Accelerators are nice, and lots of you are working on accelerators, and I love you. But it works well if your problem fits, but many problems don't fit. Industry has realized that they need to continue improving core microarchitecture research. Low-hanging fruit was picked years ago. I review for conferences a lot of reinvented wheels. What should be our goal? New ideas for industry to improve processor performance and efficiency. But do the research right. New ideas are more important than incrementally combining the old ones. Industry can combine old ideas all by itself. Try to keep complexity to a minimum. Special weird things, filters and thresholds can lead to overfitting. Use lots and lots of benchmarks to guard against that. As Einstein says, everything should be made as simple as possible, but no simpler. Be mindful of previous work, read a lot, compare experimentally to previous work. Understand the constraints of industry, do an internship. That goes for faculty too. I spent some time in industry, it really opened my eyes. Don't work on crap, aim for top tier conferences, good conferences. Be good, don't cheat, no cherry picking, unrealistic parameters, conflict engineering. Have a healthy lab culture. What worked for your advisor in your abusive situation might not work for you. Don't do that. Be nice, be good to your students, they're people. review the research right. Sometimes a 2% speed up in single thread can be just as exciting as 100% speed up from a low-hanging fruit in other domains. A 1% speed up in industry on the realistic simulators they use is cause for dancing in the cubicles. They love that these days. Speed up should be backed up with other measurements and many benchmarks to distinguish the speed up from noise. Incremental is not necessarily a bad word. It could mean a simpler solution with the same benefit as previous work, a slightly more complex solution with a surprising benefit. Don't shy away from what other people might call incremental. They called I have in a previous version of this talk, I can show you the reviews for the first paper, and this is incremental. You know, it wasn't incremental. A good idea is better than numbers or a totally feasible implementation. If I were concerned with feasibility, we wouldn't have perceptron predictors. Industry will figure it out if it's worth doing. Most of the folks, the graduate students aren't seasoned RTL engineers anyway. So give industry the good ideas and don't worry too much about the implementation. Have a path to implementation. Okay, so on to me. So I grew up in San Antonio, Texas. Turns out I'm not the first Hispanic recipient of the Bob Rao Award, and I'll leave you to go look at the other recipients and try to figure out who it is. My father was a Mexican immigrant. He became a US Army surgeon, went to Vietnam. My mom was a nurse. She met my dad in a San Antonio hospital. I started coding as a kid in assembly language on a Tandy color computer when I was real little. I stayed in Texas for higher education. I was afraid to leave Texas. I went to UT San Antonio for my master's and bachelor's, UT Austin for my PhD. And I was lucky to end up in front of you today. So how did I get to today? I learned about branch prediction during my master's studies at UTSA in 1992. Then I went to do my PhD at UT Austin. I took a class in artificial intelligence from Risto Mikulainen, who he didn't want to talk about artificial intelligence. He just wanted to talk about neural networks. That was his special thing. We had neural networks back in the 90s. Then I went to work in a rehab medicine department at the UT Health Science Center, where they had medical imaging problems that it turned out I could solve with neural networks. Because I took that class with Risto, I knew how to solve the problems they had in medical imaging. Then I came back and finished my PhD with Calvin Lynn. I tried to apply neural networks to the compiler. That didn't work out so well. It turned out Brad Calder had done all that before. But then I came up with the idea to do branch prediction with perceptrons. It was rejected from ASPLOS 2000 because it was considered too incremental. I don't know how it was too incremental, but reviewer number 1 can explain that for him or herself. Then it was accepted to HPCA 2001 and then won the Test of Time Award a couple years ago. I graduated UT in 2002, got my first job at Rutgers as an assistant professor, continued working on branch prediction. They'll tell you don't work on your dissertation after you graduate, but I couldn't help myself. I really like it. So I kept refining neural branch predictors. I had my students working on compiler and architecture stuff, but not branch prediction because I knew that was not good for them. I spent a lot of time myself working on branch prediction. Had several single author papers. Couldn't stand the weather and there wasn't any good Mexican food in New Jersey, so I came back to Texas, joined UTSA, and eventually became department chair. I was approached by Samsung. They wanted someone to build a perceptron-based branch predictor for their new SoC. So I did that and I learned a lot there. We had a paper last year in ISCA on that experience. I moved to Texas A&M. My wife had a baby and it turns out it's really hard to be department chair and a new father at the same time. And I wanted to stay in Texas and have a good research career. Now I'm brave enough to have some students looking at branch prediction. Elba Garza, who is familiar to many of you, is my student who happens to be working on branch prediction, and she's looking for a job. Hire Elba. So what did I do? A branch predicting perceptron finds correlations between the history of branches and the outcome. It's a different way of looking at branch prediction compared to what we did before. We use the same input features, branch history, 1 means yes, 0 means, or 1 means taken, 0 means not taken. And then these small integer weights are learned online with perceptron learning. It could be the dot product of the history and the weights, threshold dot product, predict taken if the output is above the threshold, not taken otherwise. That forms a linear decision surface that best separates taken from not taken branches. This little idea, we presented that in HPCA and expanded it. I expanded it, other authors expanded it to what we have today. It allowed use of much longer histories than previous work, and that gave improved accuracies. It changed the trade-off in resources in branch prediction, so you could have longer histories and it made sense. So we introduced this thing, Calvin, Lynn, and I introduced it in 2001 in HPCA. Since then, I and others introduced using hashing and path-based history to overcome linear separability problems and latency problems, improved accuracy. Andre came out and incorporated a lot of the work into TAGE and TAGE SCL. TAGE SCL uses perceptron predictor as a component, as the statistical corrector is a perceptron predictor. I came out more recently with a multi-perspective branch predictor that has many features that are optimized by a genetic algorithm. So continue to apply machine learning to improving microarchitectural prediction. Today, you can buy processors that have perceptron branch prediction, all recent AMD processors, some IBM processors, Oracle. I don't know if they're still making processors, but the last time they did, they had perceptron predictors. And then I designed the conditional branch predictor in the recent Samsung Exynos system on chip. So over the years, accuracy has been improving in branch prediction in general. On the x-axis here, we have the year, and the y-axis, we have MPKI, mispredictions per 1,000 instructions, so lower is better. And so things have been getting better really well up until we get to about 2016. And you can see TAGE SCL plus IMLI, that's Andre's predictor, and then multi-perspective, that's mine. They're pretty close. And since then, there haven't been a whole lot of, we're working on it. I'm working on it. I'm making it better. I made it better, but I haven't published it yet. Coming to a conference to you, near you soon. So we've been working on applying perceptron learning. I do a lot of stuff, but this in particular is important to me. We work on using perceptron learning in microarchitectural prediction. We've done reuse prediction for improved last level cache replacement in a couple of papers. We used it for indirect branch prediction. It turns out you can use perceptrons to do indirect branch prediction. We have used perceptron learning to do data cache prefetcher filtering. So you have an aggressive prefetcher. You can filter the unlikely to be helpful prefetches with a perceptron. And then most recently, we've done side channel attack detection. So my student, Samir Miragar, came up with this idea of using perceptrons to detect whether the system right now is under attack using all kinds of microarchitectural features. And it's a very low cost, low overhead system that I think is really cool. It has a lot of potential. If we generalize this, we can use it as just a way of using machine learning to manage what's going on in the microarchitecture. Okay. So my career has been shaped by many mentors and colleagues, too many to list for fear of omitting someone. There are so many people out there who have helped me and encouraged me all throughout my career, from my undergraduate to from before then, from high school and undergraduate and graduate school, and in people I meet at conferences. So thank you to all of you. You know who you are if you've encouraged me in my career. Thank you. There are a few people I would like to thank in particular who have meant just a lot to me. My master's thesis advisor, Human Art. I took computer organization with him at UT San Antonio in 1989. It was the most fun class ever. I loved that class. We did it on a VAX 11. It was very fun. I'm teaching that same class today. I was supposed to teach it today. I had to cancel because of this thing. Teaching computer organization. I still love teaching that class. He was my thesis advisor. He encouraged me. He pushed me to be the best I could be. He was one of the best educators I've ever known. He recently retired. He's still around at UTSA. Calvin Lynn was my PhD advisor. He was exactly the right person to advise my PhD, although neither of us really realized it at the time because he was a compiler guy. What is he doing advising this person doing microarchitecture? Well, there were microarchitects in our departments that helped us out. But Calvin really helped. I mean, he was leading the research. He believed in me, and he still believes in me. We still talk a lot. He's also one of the best educators I've ever known. He's just a really excellent teacher. If I'm a good advisor at all to my students, it's because of what I learned from him. So thanks, Calvin. And then Andreas Sesnak, my fierce competitor and my friend. We seek each other out at conferences and hang out and talk. He won this award last year for branch prediction and cache stuff. Through our work, we traded ideas and made branch prediction better and almost impossible to research for other people. My apologies if you've entered branch prediction research and found it difficult, but it's my fault and also Andreas' fault. Every time there's a branch prediction contest, I know I'm going to lose several months of my life, and so is Andre, just to trying to beat him. Today's processors use a combination of our ideas. So this is, I guess, a good place to stop, and almost on time. I tried to make it short because I knew we went out of time. But thank you so much for the award. It means a lot to me, and I'll see you guys around at Micro.
Congratulations, Daniel.
Thank you.
Amer, now we start the two parallel sessions, right? The 8A is in this track, and then the 8B is in the other one. You can go directly through the WHO agenda. Thank you everyone for attending the award session, and congratulations again to all the winners of the different awards.